Welcome back. This lecture could have served as an introduction to ESO thermodynamics, because what we want to be doing here is connect the notions which you have from your classes in classical mechanics to what we want to be doing in ESO thermodynamics. So that's subjective. So let's look at the main things which you've learned in classical mechanics, right? The most elementary things which you've known from high school is Newton's first and second law. Newton's first law is the law of inertia. We have a notion of isolated object. Somehow we can isolate the object, and the momentum of the isolated object is unchanged. That's the Newton's first law. When you go to Newton's second law, we are connecting forces acting on the object to the acceleration of the object. The proportionality constant between forces and acceleration is what we call as the inertial mass. It's just actually a proportionality constant. If the masses are somehow measured, we don't discuss on how we are going to be measuring the mass, but we have this notion of inertial mass. And we also say, what if you ask what is the force? We say force is what satisfies F is equal to ma, right? There is some kind of a circular logic. To define mass, we are going to use force. To define force, we are going to use mass. Okay, so that's the way it is. We are not going to go deeper into this. So there are lots of sources of force field. For example, gravitational force is expressed in this manner. So here we have, again, masses. We call this gravitational masses. So there is this general principle of equivalence wherein we say that the inertial mass, which we are using in F is equal to ma, okay, and the Newton's first and second law, is the same as gravitational masses. Okay, so that's been tested experimentally. That's been found to be true. So there are other force fields, sources of forces, which need not involve masses. Okay, so there can be electrical sources, magnetic sources, and so on. These are qualitatively differ from gravitational force, and there is both repulsive and attractive components, whereas in gravitation there's only attractive component. So we have also the notion of work, which from classical mechanics. Intuitively, all this notion of work is born out of physiological work. So whenever we perform work, we are doing it against a resisting force. So we have this notion of force. Work is can be expressed as resisting force times distance. Okay, this is just a elementary notion, so we can keep the discussion at this level. So we also asked the question: can this work done in a purely mechanical system? We'll clarify what I mean by purely mechanical system in a few slides. Can it be recovered? So the question can be rephrased in the following manner. It also has the answer. So supposing I have already lifted the mass, okay, so I've done work onto this object. In principle, this object can be lowered to lift another mass, right? So in that way, at least in principle, the work done can be recovered more or less fully, right? So in complete recovery of work done is possible into another form of work. That's, that. And then we also go beyond work to define what is kinetic and potential energy, again, in a simple mechanical system. So for example, if there is a cricket ball in Bumrah's hand, okay, it has potential energy. What exactly do you mean by that? At a particular position, in this case, Bumrah's hand, ball has the potential to gain kinetic energy when accelerated or when there is an applied force on the ball, right? So in this case, Bumrah is applying the force. So we define potential energy as the stored energy capacity of a mechanical system, okay, stored at a particular position. what we, by mechanical system, we are talking about an object in a force field. Okay, so that's what you mean by mechanical system here, simple mechanical system. So what I'm trying to do is, we are all used to these notions of forces, work, kinetic, potential energy. We're just revisiting it so that these terms are clear before we get on with thermodynamics. So when we say kinetic energy, uh, that is the capacity to do work is again present in that system, but it is present in the object in the form of motion of the object. For example, cricket ball with the kinetic energy can move against a resisting gravitational force, right? So again, it has a capacity to do work. All right. So here, work mediates transformation of kinetic energy to potential energy, right? So we have, again, notions of conservation of energy and work energy theorem in your classical mechanics. Okay, so all these things you've seen from high school. So we're just revisiting these notions here. All right. So this interconversion of potential energy to kinetic energy is very useful. Okay, so it's one of the earliest energy conversion device. For example, if you're thinking about, if you look at an hydroelectric power, hydroelectric energy conversion device, there is actually this interconversion of potential energy into kinetic energy. So who is giving you the kinetic energy? Actually, solar energy did all the lifting for you. Okay, so it lifted the water, gave water its potential energy in the form of clouds, right? So that's the potential energy you have after evaporation has been done by using solar energy and probably light or so. So the potential energy released is transformed to kinetic energy of the rain, which is not typically used for work. However, when rain is at rainwater falls at a higher altitude, that can be used for doing work. Okay, so that's the essential principle of hydroelectric energy conversion device. So this is fairly efficient. Okay, so typically the hydroelectric power plants can operate at 85% efficiencies, because this potential energy can potential energy form of stored water at a higher altitude can be very efficiently converted to electrical energy. Okay, so which is more usable in especially in terms of more transportable. Okay, so I'm not even thinking about using electric energy to drive an electric car. Okay, but electric energy is more easily transportable. Okay, so this energy conversion and transport of energy is a big deal. So electrical energy offers a simple way of transporting energy. So energy density, however, in hydroelectric system is very less. Okay, so the energy release per unit mass or volume is very less. That's the main disadvantage. Even though the energy conversion efficiency is fairly high, compared to other forms of energy, the energy density is very low. So that is the disadvantage. So we'll be looking at these kinds of trade-off often in this course as we go along, because thermodynamics, right from the early days of thermodynamics, historically, if you see history of thermodynamics, this notion of which form of energy is better and in what way it is better. Okay, so this trade-off was often analyzed. Okay, so this still a big issue. Energy is one of the biggest issue in current engineering. So we'll be often looking at these questions. Okay, so and which form of energy has higher value, in what manner it has higher value. So we've used this term simple mechanical system often, right? So what is a simple mechanical system? So if you look at our definitions, we have never referred to friction. Okay, we have never referred to heat. Again, we have not referred to any temperature when we talk about a simple mechanical system. Okay, so that is the way the simple laws of classical mechanics are introduced to you by using a simple mechanical system which doesn't involve friction heat or temperature. So we can differentiate two kinds of quantities. The quantities that are present in this simple mechanical system versus the quantities which we'll be seeing here, okay, in this course, thermodynamic quantities, which the central actor in thermodynamic quantities, again, is the temperature. So in fact, the objective of this course is how do we extend notions of work energy theorem, conservation and conversion of energy, as is seen in a simple mechanical system, to a thermodynamic system. Okay, so that's the objective of this course, ESO thermodynamics. Okay, so that's, again, this whole lecture could have been a brief introduction. So we are at a particular point in the course where we are going to go into thermodynamic first law. So I wanted to reintroduce this course in terms of what you already know used in classical mechanics. Thank you.